Hi guys, good morning. Shall we start? Is everyone ready?
Yeah. Good morning, sir.
Yeah. Good morning. So we were seeing colloidal state, right? So we'll continue. Okay. So I think we saw what are the different classification of colloids, right? First was based on what is the phase of dispersed medium and dispersed phase. In that I had so many salts, aerosols, emulsions, gels, foams, all these things we saw. And then we went on to see based on the size or how they are prepared, right? So I have multimolecular, macromolecular, and associated colloids, right? And then the third classification is based on whether the dispersed medium and dispersed phase love each other, right? So in that case, I had lyophobic and lyophilic colloids, right? Okay, so then we went on to see how do you prepare colloids, right? So Bredick's arc method, right? And then it was chemical methods using decomposition, oxidation, reduction, right? And then we went on to see what are the purification techniques, right? So obviously, when you prepare the colloid, it will not be of required purity, so you have to purify it. So we went on to see dialysis and electrodialysis, and there was one more thing called ultrafiltration, right? So you use a special filter paper there. I told you there's something called as collodion solution, so on and so forth, right? So the last thing which is left out in this, right, is what is my properties of colloids, right? Okay, because we already know certain properties, isn't it? So we'll go on to it. Cool. Right, fine. So looking at the properties, right? So we already know, I'd say approximately when I talk about the size of colloidal particles, I know it is say from approximately 1 nanometer to 200 or 100 nanometer. So you can see that the range is varying, right? So generally I tell that it is 1 nanometer to 100 nanometer, but 100 to 200 is also accepted. Sorry, 1 to 200 is also accepted. So that's the first point you have to know, right? And obviously, if it is a normal filter paper, colloidal solutions will not be able to pass through it, right? So that is one thing. And yeah, so second, like this is one thing, and the second thing is filter paper, right? Third one is a very, it's an optical property. It's called Tyndall effect, right? Okay, so you would have already studied about Tyndall effect in lower classes, right? Say we just say that Tyndall effect you will be able to see when there is a lot of smoke and there is some light, some amount of light present, right? So it's like, or how do I explain it? Is say I have something in the beaker, right? And if I have some light rays going to fall onto this, right? So we know what is going to happen depending on the solution, right? Depending on what is inside this beaker, right? So if at all you are able to see the light rays passing through this, right? If at all you see that the light rays are passing through this, if you're able to see it, right? So that is what is called as Tyndall effect, basically, right? Or technically speaking, Tyndall effect is the scattering of light, right? Tyndall effect is the scattering of light when it hits when it gets bombarded with a certain particle. In this case, it is going to be colloidal particles, right? So this scattering of light is going to happen. So it's like this. So if I have a colloidal particle here and say this is the light coming, right? So once this hits this, it is going to disintegrate into so many smaller rays of light, right? So this particular effect is what is called as your Tyndall effect, right? So in simpler words, how will I put it? If at all you want a definition, I can give you. 1 second, I'll give you a proper definition. Yeah, very simple. The process of scattering of light, the same thing. So it's this process of scattering of light by colloidal particles is what is called as Tyndall effect. Okay. So this will happen. This will not happen for your true solutions, right? So the thing is, there are two things you have to look into. Two things which has to be satisfied for Tyndall effect to happen, right? So first one is definitely based on what kind of light you use, right? So that will definitely, we are not going to look into it. Like the wavelength of the light, all these things matters, right? And it also going to depend upon the size of the particles, right? So the thing is, please understand that the size of the particle should be at least approximately equal to the wavelength of light used, right? So the wavelength of the light used, lambda, right? The wavelength of the light used should be approximately equal to the size of the particle. Only then I would say the Tyndall effect is possible. This is a condition for Tyndall effect to happen, right? The size of the particle should be equal to the wavelength of the light used, right? So that's a necessary condition, right? So if it is going to be your colloidal particles, yes, the particle size is little bigger, right? The particle size is little bigger, so scattering can happen, right? But if it is going to be a true solution, the particle size I know is very small, like so. This scattering of light is not going to be possible then, right? That means what I'm telling you is, if it is this is going to be a true solution, you will not be able to see anything like this, right? You will not be able to see anything like this. You will not be able to see the path taken by the light rays inside the solution. That will not be possible. But if it is a colloidal solution, yes, right? So that's what is about colloiding. Sorry, what is that? Tyndall effect, right? Okay, next is, so that's about size. Filter paper, size should be in this range. They cannot pass the filter paper, and then this is my Tyndall effect. Okay, we'll move on. Okay. The next one is what is called as your Brownian movement. Right. Next one is what is called as Brownian movement. Okay, fine. So what is this Brownian movement? The reason for why this is happening, still research is going on. Okay. What I mean, basically, why that Brownian movement happens. We know what is Brownian movement. That I'll tell you, right? But the reason for this, there are so many theories proposed, but none of them give a say a satisfactory explanation of why this happens. Fine. First, we'll see what is this. Okay. So if I observe my colloidal particles, say I have a vessel in which I have some colloidal solution with me, right? And I take a very small sample of it and I visualize it under a very strong microscope, right? So what scientists observed is that, say, if this is a sample and inside that I have so many colloidal particles, so they saw that they are undergoing some random motion like this. So it's zigzag motions are happening, right? So that's what is called as Brownian moment. So now, if at all you want me to properly define it, right? So it's very simple. It's the zigzag movement of colloidal particles, and that's the simplest way to put it. It is the zigzag movement of colloidal particles observed under a microscope. Like that is what is called as Brownian moment. And why Brownian moment? Because Brownian, Robert Brown was the scientist who was attributed to this discovery of Brownian moment, right? Okay, so so what could be the reason, right? What could be the reason that this kind of movement happens inside, right? So one possible explanation can be, I obviously know that all the particles, whatever the type of solution is, they will undergo some type of collision, isn't it? Right? So here also that's the reason. That is the reason, right? So here also I'm going to have some kind of collision, right? And what is the most accepted theory is that it is because of unequal collisions between, unequal collisions between the colloidal particles. So that's the reason. So say for the first collision, I have say 10 particles with me, right? Say the first particle goes and hits the second particle in the say the velocity of some x meter per second, right? So after hitting it, say the first particle comes back with say some y meter per second, right? And obviously it is going to go hit the third particle. After hitting it, it is going to come back with z meter per second. So you'll obviously see that after each and every collision, the velocity of the particles changes, right? So not all collisions are same, right? But ideally speaking, I don't know whether you would have studied in your kinetic theory of gases in your 11th class. So they say that all collisions are elastic in nature, perfectly elastic collisions. No, that is in real life. That is not how it's going to be, right? So that definitely are going to have different kinds of velocities. Say after each and every collision, the velocities of the particles are going to change, and thereby I'm going to have this zigzag moment called Brownian moment happening, right? So that's again another property of colloidal particles, Brownian moment, right? Cool. Next, right? So actually, there are so many things. There are so many other properties which are not there in the syllabus for you. Actually, what I'll be able to do is the entire properties of colloids can be uh, classified into classified into three ways. There's the first one of what are called as optical properties, right? So under optical properties only you have your Tyndall effect, right? So this is my Brownian moment and all comes under your kinetic properties, something related to movement, right? And now we are going to see something called as electrical properties, right? So if I supply some electricity, or it is going to be in the form of some charges, right? So all these things we'll see now, right? Good. Okay, so we're going to see the electrical properties, right? So under this, right? So what people observed is that, say I have, so what you're going to see here is that there are going to be some charges developed on the colloid. Okay, there are going to be some charges developed on the colloid. So we are going to see how is it going to happen, or like not exactly how is it going to happen. Like we'll see at least how to make the colloid have a charge on the surface of it. Right. Say what I'm going to do is, say I have your AGI colloid with me. Okay, I have colloid. This is a colloid salt. AGI colloid I have with me. Right. So to this, what I do is, to this I add your NaI solution, electrolyte. Right. So this I add your NaI solution. Okay. So now what is going to happen is, so you see that the common ion here, right, in both of these AGI and NaI, the common ion here is iodide, I minus, right? So I have excess of iodide ion present, right? I have excess of iodide ion present. Okay. And so what is going to happen is, say if this is one molecule of AGI colloid, right? If this is one molecule of AGI colloid, so you will see that there will be so many I minus ions surrounding it. So this kind of thing is going to happen, right? So why this happens is because I have iodide in excess, right? So that's why you see that a negative charge, like on the surface of the colloid, you will see so many excess of negatively charged particles, and in this case, it is going to be iodide, right? So this is what is going to happen, right? So this can even happen for positive things also. Say for example, um, if I can give you some examples. Yes. So another example can be, say I have FeOH thrice, right? I have FeOH thrice. I know we have already seen this as examples for colloid. And if I mix them with, say, FeCl3 solution, This is again an electrolyte, right? So this is my colloid. Right? This is my colloid. FeOH is my colloid, and to that I add FeCl3 solution, right? Now what you can see is the common ion here is Fe3 plus, isn't it? The common ion here is Fe3 plus. So exactly opposite of what you saw here is going to happen. Say if this is my FeOH thrice colloid, right? Surrounding this, I'm going to have Fe3 plus ions everywhere. Right? So they're going to surround your FeOH thrice molecule like this, right? So this is what is called as charge developed. This is how the charge is developed on the colloid, right? So if at all you don't have anything extra, right? That means say if at all I have only AgI, if I have only FeOH thrice, this might not happen, right? So you have to have some extra, extra electrolyte which is going to have a common ion, either positive or negative. That depends, right? But that has to be there, right? Some extra electrolyte which is going to supply you the negative charge or the positive charge should be there in order for you to see some arrangement like this. Okay, right? So I can have a negatively charged colloid or say a positively charged colloid depending on what electrolyte you add. That's what is very important. It's not like randomly I can say that it is going to be negatively charged, or randomly I can say that it is going to be positively charged. It definitely depends on what kind of electrolyte you add to that particular colloid. Understood, right? Cool. Now this is not where it is going to stop. Okay. So obviously, I know charged particles are a little unstable. So isn't it, compared to neutral particles, right? Charged particles are always little unstable, right? So in order to attain stability, right? In order to attain stability, what is going to happen is, right? This is not going to end up here. There is some more things which are going to happen. What do you expect to happen? Say for example, in this case, I have this, right? I'm telling this is not going to stop just like that. So what do you expect to happen here? Any guesses? No guesses. No
Will it
guesses?
become unstable?
Yeah, that's what it is. Already unstable. To attain stability, what it can do? That's what I'm asking.
Has to gain the same amount of positive charge somehow.
Exactly. So that's the very good probability, and that is exactly what is going to happen here, right? So what is going to happen is, so since I have excess of negative charge on the surface of this colloid, right? So what is going to happen is I'm going to have some positive charges surrounding the first layer, making a second layer of charges, right? This is going to happen. Same way here. Since I have totally positive charges surrounding in order to attain stability, so you'll see that negative charges are surrounding each of these Fe3 plus ions, making a second layer of charge, right? But again, there are going to be certain differences between the first layer and the second layer. Okay, fine. So let me go into the technicalities of this. Right. Say the first layer of charge is what is called as your compact layer or fixed layer, right? And the second layer of charge is what is called as your diffused layer. So I think from the words, from the terms, you can understand what I'm trying to say, right? So your first layer, that is say in this case iodide layer, is fixed. It will not be able to move and all that. But since your second layer is little away from this colloid, right? So this is a diffuse layer. This will be able to move there and there, right? So that's what you need to understand, right? The first layer is always going to be a compact or fixed layer. Second layer is a diffused layer. That means it can move little bit, right? Okay. So now the thing is, obviously, you can see that, say for the first layer, say I would have had a potential developed, isn't it? Right? I would have had, I'm not telling potential difference, I'm telling potential, right? So obviously, when you have your charges, you would have studied in your electrostatics, right? So I will have your potential depending on what is the magnitude of charge, 1/4 pi epsilon naught Q divided by Q and Q2 by R. Am I right? Is it correct?
Yes, sir.
Okay. It's been so long since I studied physics. Anyways, so the thing is, if I have some charges, I will have some potentials associated with them, right? So obviously, I assume that the first layer has a potential of V1. For the second layer, say the potential it is V2, right? So obviously, what I understand is there is going to be some potential difference between the first layer and the second layer. So I'm talking about V1 minus V2, right? I'm talking about V1 minus V2. That means what? The first layer has some potential, second layer has some potential. So there is definitely going to be some potential difference between the first layer and the second layer, right? So this potential difference, right? This potential difference developed between the fixed layer and the diffused layer is again going to be a technical term, which you have to know is what is called as zeta potential. Right? So what is zeta potential? Zeta potential is the potential difference developed between, that is potential difference between the first layer, or you should not say first layer, it should be fixed layer or compact layer and the diffused layer. Between those two, definitely they'll have their own potentials and they will have their potential difference, and that potential difference is what is called as your zeta potential. Okay, right? And one more technical term I'm going to give you, right? So you see this double layer of charge, isn't it? This, you see this double layer of charge. So this double layer is also called as Helmholtz double layer. Helmholtz electron double layer, or just the double layer? Double layer, that's it. Helmholtz double layer. Okay, so Helmholtz double layer is that nothing but the two layers of charge together is called Helmholtz double layer, and the potential difference between these two layers is what is called as your zeta potential. Okay, fine, right? So that's about the charge which you have to know, right? If at all you want to study further, I will be able to even calculate the charges. There are some formulas for it, again, not for you, higher levels of chemistry, right? Fine. Okay, so now we will see what and all we can do with this, right? So because of this, because you see that there is going to be some positive and negative charges, are going to be, there's going to be some double layers. If I apply some external potential, right? If I apply some external potential, you will see certain things happening, right? So we'll see what are all those things. Okay, so we are going to see again a technical term here. See guys, this particular chapter is all about definitions, right? So you have to know the proper definition. That is where the questions will come also, right? Max to max, you can get questions from this chapter in max, like say a 2 mark or 3 mark, right? So that's the maximum number of marks you'll be getting. Maximum number of marks you can see from this chapter. So it's very easy. You just have to understand the concept and understand the definitions if you have, and that's it. You're ready to go. It's very simple. Anyways, so we'll move on. So we are going to see what is this electrophoresis. Okay, electrophoresis. Take to the definition first. Take to the definition. It is the movement. It is the movement of colloidal particles. It is the movement of colloidal particle under the influence of an external electric field, right? It is the movement of colloidal particles or it is a phenomenon of movement of colloidal particles. It is a phenomenon of movement of colloidal particles under the influence of an external electric field. Under the influence of an external electric field. Is that okay? Very simple, right? Obviously, say if I have okay, I'm not able to give you the proper diagram, but still, say this is a colloidal particle, and say this is inside this I have a colloidal particle, right? So now what will you see? Say if I switch on the battery, and obviously I should know that this colloidal particles can be charged. It can either be positively charged or it can be negatively charged. Again, now we are not going to take into the account of your double layer, right? So we are going to see what is the fixed layer, and obviously fixed layer will have more charge, isn't it? The fixed layer will have more charge compared to the second layer. The second layer is little diffused also. We already spoke about it, right? So depending on what is the charge possessed, charge possessed by the colloidal particles, obviously the direction of movement will be different. For example, if it is going to be positively charged, it is going to move towards the negative electrode. In this case, the negative electrode is here, right? And obviously, if it is going to be negatively charged, it is going to move towards the positive electrode, right? So this movement, so this is an electric field which is applying, right? So because of the charge possessed by the colloidal particles, if you apply any external field, the colloidal particles will start to move. This movement, this phenomenon of movement of colloidal particles under the influence of electric field is what is called as your electrophoresis. Phoresis means movement actually. Electrophoresis means because of the electric field, the movement is happening. Right? That is what is called as your electrophoresis. Right? Again, this is another property of your colloids because of the charge basically. Right? Okay. And next one, very, very similar to this, is electroosmosis. Okay. What do you mean by electroosmosis? The same thing I can do, except that I'm going to have a semi-permeable membrane in between, right? I'm going to have a semi-permeable membrane. So how do I define it? Please go for the definition. Same thing, it is the phenomenon of, oh, wait, 1 second, people. Okay, so here it is little different. So they say that the dispersed medium is, no, we'll not go into the details of it. Please check on the definition. Here the only difference is, say I can have one more compartment. Say the simplest way to put it is like this. This is my SPM. Right, again here also I have my colloidal particles. So something like this, right? This is my cathode, anode, right? So now here you see there is a, what is that? There is a semi-permeable membrane. So dispersed medium from this side to this side, or say dispersed phase from this side to this side, depending on where the potential is higher, right? Depending on whether it's a positively charged colloid or a negatively charged colloid, the direction of movement will be different. So the only difference between electrophoresis and electroosmosis is the presence of a semi-permeable membrane, nothing else, right? So you just see that again. How do you define electroosmosis? It is the movement of colloidal particles across a semi-permeable membrane under the influence of an external electric field. If you want, I'll tell you again. Please take down. Right? It is the phenomenon of. It is the phenomenon of movement of colloidal particles. It is the phenomenon of movement of colloidal particles through a semi-permeable membrane. Through a semi-permeable membrane under the influence of external electric field, under the influence of an external electric field. Right? So yeah, that's about electroosmosis, right? And with this, I would say the properties of color are almost over, right? So we just have one thing left out, right? So we're just going to convert, right? How do you convert a colloid into a precipitate, right? How do you convert a colloid into a precipitate? That we will see, and that's it. We're going to end the chapter in a few minutes. So the process we are going to see here is this coagulation, right? Please take down the definition for coagulation. Right. So the definition goes like this: it is the process. It is the process of conversion of colloids. It is the process of conversion of colloids into precipitate. Right? It is the process of conversion of colloids into precipitates. Very simple, right? Okay, so now how are you going to do it? There are so many methods available. So certain times coagulations can be coming, say if you heat the colloids, right? Or if you give some, if you expose some special light on the colloid, right? Or I would say even if you supply some electricity, right? If you supply some electricity, right? Or the most important one which you're going to study now is by adding an electrolyte. Right? By adding an electrolyte. Okay. So these four are the methods, but in our book only this would have been given, right? Adding an electrolyte, right? So if you add an electrolyte, so of suitable concentration and suitable charge, I would say, right? So why this is gonna happen, right? Why this what is that coagulation is going to happen is because you know that you are going to have some first layer of charges present in the colloid, isn't it? So if at all I add an electrolyte, which will be able to give me the opposite charge of what the first layer is, right? Which is able to give me what is the opposite layer, I mean opposite charge of what the first layer is. So they will be able to react with each other, right? And the precipitate can be formed, right? And the precipitate can be formed. Okay, cool. Right. So by adding an electrolyte, this was your what is your main thing. Okay. So anything which I have to say here. Yeah. So what you have to understand is the colloid. So for example, if I have AgI on surrounding this, I have say negative charges like this, right? So you have to add something which is going to give me a positive charge, at least say X is positive charge. I can say that you can add, say something like this. I can add some amount of sodium plus, right? I can add amount of sodium plus, or say some other amount of positive charge you can add, so that this will be diffused and this AgI will become bigger and they will go into the precipitate form, right? This will become bigger and they will move into the precipitate form, right? So you don't have to go into the details of how exactly it is going to happen because that is not important to us. So please understand that if I add an electrolyte, see, sometimes electrolytes are also added. You can see that before also I said, but how do you develop charges on the electrolyte? Like obviously I told you that you have to again add an electrolyte. Here I'm telling that again you have to add electrolyte to form a precipitate. So what is the difference here? The difference is only in the amount of electrolyte. Please understand, right? So for the development of charge, right? For the development of charge here, I require only traces of electrolytes, very small amount of electrolytes. Okay. But if at all you want to go for coagulation, that is when you want to convert the colloid into a precipitate, at that time you need excess of your electrolytes, right? So the only thing which will vary is here, that is when you want to develop a charge and between when you want to convert a colloid into a precipitate, the only thing which will vary is the amount of electrolyte. In both the cases, you are adding electrolyte, but what matters is the amount. In case of the charge development, very traces of amounts of colloid, electrolyte is added, right? But here, if you want to coagulate them, definitely I'm going to have higher amounts of electrolyte getting added. Okay, right? Cool. So now obviously I can, depending on what is the amount of charge or depending on what is the ion used, how fast I'll be able to do this, right? How fast I'll be able to do this can all be calculated, and it is also going to depend upon the properties of the electrolyte also. So obviously the only one property which I'm going to have, that is the amount of positive charge or amount of negative charge that particular electrolyte has, right? Depending on that, it is going to move, right? Yeah, so that rate which I'm talking about, right? So that is how fast an electrolyte we can convert an colloid into a precipitate, is represented by a technical term. Again, that is what is called as my flocculating value. Please again take down the definition. Flocculating value is going to talk about the electrolyte. Depending on the electrolyte, how fast I'll be able to do the precipitation. Okay, take down. It is equal to the minimum concentration. Right? It is equal to the minimum concentration. It is equal to the minimum concentration of an electrolyte required to coagulate 1 liter of sol or say colloid, 1 liter of colloid completely, right? It is the minimum concentration required, right, of the electrolyte to coagulate 1 liter of sol or say colloid completely. Right? Fine. So from this I can easily understand what is the minimum value required. Right? If I have 1 liter of the colloid, what is the minimum value required for precipitation to happen? Minimum concentration of the electrolyte required for precipitation to happen completely. Whatever the entire 1 liter should convert into precipitate. Right? So that is what it is called as your flocculating value. Minimum concentration required for the electrolyte for 1 liter of soil to get precipitated. Right? That is what is called as your flocculating power. Right? There's something called as coagulating power also. 1 second. Oh, coagulating power or flocculating power. Okay, so I have something called as flocculating power, or I have something called as coagulating power. Okay. So obviously, the flocculating power or flocculating power or coagulating power talks about how much is the ability of the colloid, or how much is the ability of the electrolyte to convert your colloidal particles into precipitate. In simple words, you can just take it, right? It is the ability, right? It is the ability of the electrolyte. It is the ability of the electrolyte to convert, or it is the ability of the electrolyte to perform coagulation. Very simple as that, right? It is the ability, both of these are same, flocculating power or coagulating power are same, right? It is the ability of the electrolyte to perform coagulation, as simple as that, right? Okay. So how do we compare, right? How do we compare the flocculating powers of different ions? So please understand that for a positive colloid, right? For a positive colloid, you need to use a negative ion for it to coagulate. I already told you. The oppositely charged ion should be added in order for me to have precipitation, right? Say if at all the colloid is positively charged, you need to have a negatively charged electrolyte present, right? And obviously, if I have so many types of negatively charged colloid, so please understand that the flocculating power or coagulating power is directly proportional to the charge of the electrolyte, right? It is directly proportional to the amount of the positive charge or amount of the negative charge possessed by the electrolyte. This you have to know, right? The flocculating power or the coagulating power is directly proportional to the charge. Okay, so if that's the case, say for example, if it's a positive colloid, say I have SO4 2 minus, NO3 minus, say I have, okay, I'll just take like this, NO3 minus, SO4 2 minus, PO4 3 minus, all these things if I have, right? So these are different anions which will be able to coagulate this positive colloid, right? These are different anions which will be able to coagulate the positive colloid, right? So among this, which will be the best, or which, if I want to compare the coagulating values, so I mean coagulating powers, right? So I already told you that the flocculating or coagulating power is directly proportional to the charge. So obviously PO4 3 minus will be having more coagulating power than SO4 2 minus, and SO4 2 minus will have more coagulating power than NO3 minus, right? And lastly, so when I have a negative colloid, you need to use an electrolyte which will give me a positive charge, right? Say if I have Al3 plus, Mg2 plus, and Na plus, again same thing, more amount of charge, more is the coagulating power. So Al3 plus will have more coagulating power than Mg2 plus, and Mg2 plus will have more coagulating power than Na plus, right? And how do you compare flocculating value and flocculating power, right? So flocculating value talks about minimum concentration. Say for example, there are two colloids with me, right? There are two colloids with me, right? Say the first one, both of them are positive, assuming that both of them are positive colloids. Okay, fine. Say in the first case, both of them contain 1 liter, right? Both of them contain 1 liter, and both of them are, I would say, positively charged colloids. Okay, so, or let me see it in this way. Okay, let me look at it like this. Okay, say I have the same positive colloid in two things, right? I have the same thing. Say I have, for example, positive colloid FeOH thrice in both of them. Same 1 liter, same concentration, everything is same, right? Say to this, I add some X1, or I would say, okay, some X1 electrolyte, and to this I add some other electrolyte here. Okay, so here I add some electrolyte, here I add some other electrolyte, but here the colloids are same. FeOH thrice is the colloid in both these cases, and both the vessels are of 1 liter, so no problem about that, right? Okay, so what I find here is that here I require, say, 1 m of electrolyte, and here I require, say, 1.5 m of the electrolyte for me to have coagulation happening, right? For me to have complete coagulation happening, right? So I mean, this is telling, I mean, this is requiring 1 m solution of an electrolyte, and this requires 1.5 m of the electrolyte, because these two are different electrolytes. I'm telling, right? This is one electrolyte. This is another electrolyte. This electrolyte 1 m is sufficient, but for this electrolyte I require 1.5 m. Right. So now tell me, looking at this, so the flocculating value is understood from this. Both of them are 1 liter, right? The flocculating value here is 1 m, and for that it is 1.5 m. Now think and tell me how flocculating value and flocculating power are related. You think and tell me. Flocculating value and flocculating power, how is it related?
The higher the flocculating value, lower the power, something like that.
Correct. Exactly right. So the thing is, whichever electrolyte which will be able to do the coagulation with minimum concentration, right? Say I can eventually do the coagulation if I have even so much amount of what is that electrolyte, right? But the point is, if I talk about the coagulating power, with smaller amounts itself, it should be able to coagulate, right? With smaller amount of electrolyte itself, it should be able to coagulate. So it's very easy to understand, guys. Please understand that flocculating value and flocculating power, flocculating value and flocculating power are inversely related, right? Flocculating value and flocculating power are inversely related, right? What is the requirement? Smaller amount itself should be able to give me higher values of coagulation, right? So flocculating value and flocculating power are inversely related. Okay, so I think that's about the chapter, right? So, and obviously one more thing is left out, that is about the applications of colloids, and that's for you to study. Okay, where non colloids are used. There's something called as cisplatin. So many things, I have, they are used in masks. So lot of places they are used. So it is up to you to go and study about it, right? And definitely questions can come from application of colloids also. Questions can come. Okay, so fine. What is the time? Yeah, we have almost 5 minutes left, but you can go, guys. That's about the chapter. So next class we'll be talking about solid state. We'll be starting a new chapter. Again, one last chapter, some little, again a small chapter, not like electrochemistry and chemical kinetics. It is a little smaller chapter, and but it requires a little. I told you it requires a little imaginations. When I tell you that the line passes through here, there are 3 spheres and all that. You should be able to imagine it. But even if you don't imagine it, no problem at all. We will be able to do the problems. We will be able to answer all the questions which will be asked. Don't worry. Okay. So till then, we'll see. Thank you.
Thank you, sir.
Bye. Yeah.
Yes, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you.